Hey everyone, welcome to BCP Med. In this video, we're going to explore the electronic effects which impact hydrogen bonding strength, such as the electronegativity of the atom bonded to hydrogen and the electron density of the acceptor. We're also going to look at the amount of H-bond sites a given molecule has, and of course, resonance effects. Let's go ahead and get started. Our first factor is going to be electronegativity difference. Because we know that H-bonds are an electrostatic interaction, we expect that larger positive and negative partial charges will lead to stronger H-bonding. A larger electronegativity difference between H and the bonded atom should achieve this effect. For example, let us compare water and ammonia. Clearly, water has a far higher boiling point than does ammonia. Why is that the case? Well, let's go ahead and look at the NH bond. There's a nice dipole pointing towards the nitrogen, which has an electronegativity value of about 3. However, if we go ahead and look at the OH bond, we'll see that the oxygen, or rather we'll see that the arrow is quite a bit larger, meaning that the bond is going to be more polar. This is because oxygen has a higher electronegativity than nitrogen at about 3.5. The stronger dipole of the OH bond means that the hydrogen will carry a larger positive charge than it would in ammonia, and also that oxygen will carry a more negative charge than the nitrogen would. We can also see this quite nicely in potential maps, where the size of the blue area for the H2O hydrogen is much larger than the ammonia hydrogen, indicating it carries a larger partial positive charge. Again, since the electric force is proportional to charge, larger charges are going to mean stronger H bonding. Hence, water is going to have the much higher boiling point. We can also see increasing charges in another way. We know that water has a hydrogen bond energy of about 23 kilojoules per mole, which isn't too shabby. But what if we let it bond with a species with an even greater negative charge, such as an anion? Well, this is actually a special interaction often referred to as an ion-dipole interaction. And in the case of water, it can be a form of specialized hydrogen bond. So, if we go ahead and look at the NaCl interaction with water, we'll see the following picture, where the sodium ion is going to be surrounded by the negative terminus of the water molecule, the oxygen, and the chlorine is surrounded by the positive terminus, the hydrogens. And it's this chloride anion interaction that we're really going to focus in here, because that is a special form of hydrogen bonding. Now, because of the full charges on the ions, these attractions are far stronger than the typical values that we'll see. In fact, the enthalpy of hydration for NaCl clocks in at about negative 774 kilojoules per mole, significantly stronger than the typical intramolecular H bonding interaction. This extreme case shows how important the concentration of electron density is towards intermolecular forces and electrostatic interactions writ large. Another major factor which influences H-bond strength is the number of possible acceptor and donor sites. For this, let's start off by comparing H2O and HF. In this case, the HF molecule has a larger electronegativity difference between the atoms than water. However, water again has a much higher boiling point. In fact, the boiling point of HF is more similar to ammonia than water. Why is that the case? Well, if we look at the H-bonding network of the two molecules, it might become a little bit more clear. Water, on the left-hand side, tends to form 4 hydrogen bonds using both acceptor and donor sites, the 2 hydrogens and the 2 lone pairs on the oxygen. On the other hand, hydrogen fluoride only tends to form 2 hydrogen bonds per molecule, 1 acceptor and 1 donation. Because H2O forms more bonds, it has a higher boiling point, plain and simple. In this slide, I also want to look at 2 unique examples which I think are quite illuminating. The first is the case of hydrogen peroxide, which has a boiling point of 150 degrees Celsius. The peroxide molecule looks sort of like water, except that it has 2 oxygens in the center. This allows peroxide to form an impressive 6 hydrogen bonds in its H-bond network. What I think is really cool is how the hydrogen peroxide boiling point appears to scale up perfectly from water with the number of H-bonds, which I suspect is since the Celsius scale is based on the freezing and boiling points of water. For example, water has 4 H-bonds for a 100-degree boiling point, and peroxide has a 150-degree boiling point for 6 H-bonds. Thus, it seems like each bond exactly contributes 25 degrees Celsius in boiling point. The other example I want to go ahead and look at is the DNA base pairs, which are made through H bonding. It has been observed and shown to be of biological significance that the GC base pair is actually quite a bit stronger than the AT base pair. Why is that? Well, consider the adenine-thymine base pair shown here on the left. It has 2 hydrogen bonds between the purine and pyrimidine bases. On the other hand, if we look at the GC base pair, shown right, it is going to have 3 hydrogen bonds between them. This extra H bond in the GC base pair makes that pair stronger, and so regions of DNA with more GC base pairs are going to be more stable, whereas those with more AT base pairs are going to be quite a bit weaker and easier to open up. These regions are going to be typically used as origins of replication for the DNA molecule. Finally, our last major effect is that of resonance and formally charged resonance structures. The formal charge associated with resonance structures can increase the positive or negative character of some atoms in a molecule, such as hydrogens or acceptor atoms. We can begin our discussion of how this affects H bonding by looking at formamide, which has a boiling point of 219 degrees Celsius. Now, formamide looks as follows, consisting of a mix of the 2 resonance structures shown below, one formally charged, the one on the right, and one not, which includes the double bond to the oxygen. Like usual, the formally charged resonance structure is not preferred, but it does influence the character of the molecule significantly. If you look at the potential map for formamide, you see just how blue the H's are, and that is also reflected in the very high dipole moment of the molecule, which is about 3.4 dBi, about twice the dipole moment of water, which is typically considered as very polar. What's fascinating, though, is how this alternate structure, the resonance structure, affects the character of H bonding. The positive charge on the nitrogen makes it very strongly electronegative, far more so than a usual nitrogen, which in turn highly polarizes the attached hydrogen. Conversely, the oxygen is now formally negative, making it even more attractive of an acceptor site. As such, as shown below, the molecule can form this really nice dimer between themselves, which is extremely strong, stronger even than water's hydrogen bonds. Hence, the very high boiling point of over 200 degrees Celsius. In fact, this H bond is the exact same one that holds together the secondary and tertiary structures of your proteins in your body, which is why they are so stable. Now, a similar argument can actually be made for the boiling point of acetic acid, which is higher than that of water, clocking it at about 118 degrees Celsius, whereas water's 100. If we go ahead and draw the resonance structures for acetic acid, we'll see that very much like formamide, it has the same resonance structure with a positive charge on oxygen now instead of nitrogen, and a negative charge on the other oxygen. In fact, it will go ahead and form the exact same dimer structure that formamide does, because it has a similar geometry as well. And this is actually a very common dimer structure unique to carboxylic acids and carboxy acid derivatives that they pair up in this fashion. However, a question arises here naturally. If acetic acid has a higher boiling point than water because of this resonance effect, and formamide also has a higher boiling point due to this resonance effect, why is the boiling point of acetic acid so much lower than that of formamide? Well, it's because the nitrogen in formamide is much happier carrying the positive charge than the oxygen is in acetic acid. Right? Nitrogen is less electronegative than oxygen, and so it's better carrying a positive formal charge. This means that the formamide charged resonance structure will contribute more to the overall character of the molecule. The formal charged resonance structure matters more in formamide than acetic acid, and so the formamide structure is actually going to be more polar overall than the acetic acid, and as a result is going to have more polarized hydrogens and therefore stronger hydrogen bonding. Having talked about all these different electronic effects, we've actually reached the end of our content for this video. Thank you guys so much for watching, and if you enjoyed what you saw, please like and subscribe to the channel. Make sure to check out the other videos on our chemistry playlist to learn more, and if you're looking to branch out, check out our other science playlists. See you next time!